Hello there. In this exercise we are working with this set of positive real numbers and is defined as u and v will be just positive real numbers and k will be and the scalar value will be any real value. Okay, so it could be even negative, it doesn't matter. And the point is that in this space we are going to define the summation as the usual multiplication. So the sum of two vectors in this space, that's why I'm using this different notation for the addition symbol, will correspond to the usual multiplication of numbers. And the scalar multiplication will be defined again with this different symbol. It's just I add a circle outside of the usual symbols of multiplication and summation, will correspond to powers of that number. So here I'm going to illustrate some examples just to show you how this space works with the summation. So for example, 2 plus 3 will be actually 2 times 3, that is equals to 6, and 6 plus 4 will be 6 times 4, that is equals to 24. And the same happened with the scalar multiplication. 2 times 4 will be 4 squared, that is equal to 16, and 2 and minus 2 to the power times 3 will be 3 to the power of minus 2, that is equals to 1 over 9. And here in this example you can observe that the negative number here in the scalar doesn't affect the result, because the result is still positive real number. So that is just to illustrate how this space works with these operations. And now let's see what we need to prove. So in this case, for this space, we need to prove the following. If we multiply a scalar by a vector and the result is a zero vector, that is only possible if k is equals to 0 or u is equals to the zero vector. And one important remark is that in this space the zero vector corresponds to the value of 1. So you need to be really careful to not confuse the zero vector with the number 0. That's not true in this case. So let's start with the proof. So the first thing is to assume that k is different from 0. So if k is different from 0 and k times u is equals to the zero vector, this is equivalent to say that u to the power of k is equals to 1. But k is different from 0, and the only possible solution for this equation here is that u should be equals to 1, because 1 to any power different from 0, and even 0, is equals to 1. So u should be equals to 1, that is actually the identity or the zero vector in this space. So we have shown the first step of this proof, that if k is different from 0, then u and I always forgot the other thing, and k times u is equals to 0, then u is equals to the zero vector. And here's also the zero vector, that in this case is 1. This is 1. The next is to show what happens if k is equals to 0. So if k is equals to 0, then and k times u is equals to the zero vector that we know that is equals to 1, then so if k is equals to 0, then what happened with u? Well, if k is equals to 0, we have that u to the k will be equals to u to the 0, and this is equal to 1, which is actually what this statement said, and this is true for any u in this vector space, even u non-zero. Okay, because any real number to the power of 0 will be 1. So that proves the other. So if u is different from 0, then k should be equals to 0. And that ends this statement.